Hi, everyone. It's Dr. Lindner. I'd like to continue with blood. And I paused the last video. I was going to talk about hemoglobin in the last video, but I think I went on a little bit long. So let's focus now on hemoglobin a little bit. When we look at the word, we have heme and globin. So we know that globin is a globular protein. It's a transport protein that's going to carry iron. So hemoglobin is a conjugated protein, meaning it's a protein that's bound to another substance, and it's used by erythrocytes to transport dissolved gases. The most common form of hemoglobin in humans is called hemoglobin A. And hemoglobin is going to consist of 2 alpha polypeptide chains, 2 beta polypeptide chains, and 4 iron atoms. The iron atoms actually carry the oxygen, which is transported by the red blood cell. Each molecule of hemoglobin A contains 4 iron atoms, and each iron atom carries 1 molecule of oxygen. Therefore, each hemoglobin A molecule can carry 4 molecules of oxygen. The average erythrocyte contains 280 million molecules of hemoglobin. How about that? So when we look at a red blood cell, right, it's 8 micrometers. Here's the biconcave disc. There's no nucleus. Now we see here alpha polypeptide chain. This is the hemoglobin molecule. We see that there's heme, and then we see iron. Iron is typically Fe2+. That's typically how you'll see iron. Okay. Now, how does the oxygen that's bound to the iron, how does it know when to hold and how long to hold it and when to release it, right? Because the hemoglobin's got to bind to it, but then it's got to deliver it to other cells and tissues for energy production. Well, this is where the Bohr effect comes into play. The Bohr effect states that hemoglobin binds best to oxygen under a slightly alkalinic or basic environment. And it just so happens that the lungs happen to fit that criteria. So at the level of the lungs, the blood is slightly basic due to the higher concentrations of bicarbonate ion. And oxygen will bind very, very strongly to hemoglobin in the blood at the level of the lung. At the level of the cell, things shift, where the blood is now slightly acidic, because the cells are slightly acidic due to lactic acid and carbonic acid. And that reduced pH, right, when you have a lower pH, now it's acidic, it causes the oxygen to separate from the hemoglobin and allows the cell of the body to pick up the oxygen there. So this leads us to believe, all right, well, pH is really important. We shouldn't play around too much with it, but people do play around with the pH a little bit, especially when they use antacids. Antacids can alter the pH of the blood enough to affect the binding of oxygen to hemoglobin. Antacids can alter the pH of the stomach. The stomach needs to be acidic. If you use an antacid, you change the pH, and you need an acidic pH to absorb iron in the stomach, calcium, and B12. If it's too alkalinic, you're not going to be able to absorb those things. So we do see a degree of anemia and fatigue with people who are on long-term antacid use. Also, you need an acidic environment in order to break down proteins. And hemoglobin, globin is a globular protein. If you're putting in protein into your diet, but you don't have the digestive enzymes to break down the proteins, we're in trouble. If we're drinking high pH water, right? I said, don't fall for that fad of drinking pH water. That's a problem, because if you drink high pH water, you're raising the pH of the stomach, and then the digestive enzymes don't work properly to break down the protein in the stomach. You need acids to do that. Okay, and B12 binds to intrinsic factor in the stomach only in an acidic environment. We need calcium, can only be absorbed in an acidic environment, as does iron. So we see the domino effect here. So that's a little bit on the Bohr effect. Hemoglobin is involved in regulating blood flow and blood pressure by the release of nitric oxide, NO. Nitric oxide, or NO, causes vasodilation. If blood vessels vasodilate, then you're improving blood flow. If you're improving blood flow, you have more red blood cells, more hemoglobin, more oxygen delivery. Red blood cells also contain carbonic anhydrase, and anything that ends in ase is an enzyme, and that catalyzes the conversion of carbon dioxide into carbonic acid. And carbonic acid is going to transport about 70% of the carbon dioxide in the plasma. So here we can see this carbonic acid here, which is carrying 70% of the carbon dioxide. Now we have carbonic anhydrase working on that to break carbonic acid down into carbon dioxide and water. Okay, carbonic acid is an acid, but it can actually be converted into bicarbonate and a hydrogen ion. So bicarbonate is more alkaline, carbonic acid is a base, and the body can go back and forth to carbonic acid or bicarbonate to carbonic acid. It's a two-way street. You can see the two arrows here, depending on the pH of the body. Okay. Let's look at nitric oxide, since we mentioned it, and talk about angina. Angina, or angina pectoris, is chest pain. So in addition to oxygen and carbon dioxide, hemoglobin can carry NO, or nitric oxide. And nitric oxide is a major component of something referred to as endothelial cell derived relaxing factor. And these endothelial cells are going to line the internal surface of arteries and veins. And these cells produce endothelial cell derived relaxing factor, which will have an impact on the smooth muscle of the blood vessels. That smooth muscle layer is called the tunica media, also known as the tunica musculosa. The internal lining of a blood vessel is called the tunica interna. The middle layer is the tunica musculosa, and the external layer is the tunica externa, aka adventitia. So the relaxing factor relaxes the tunica musculosa of the blood vessel, allowing it to dilate, opening up, which increases the flow of blood to various parts of the body. So what's cool is that these erythrocytes can actually affect their own rate of flow by carrying nitric oxide. They're going to impact whether or not the blood vessels can dilate or not. Well, nitroglycerin contains high concentrations of nitric oxide. Remember, that's the key ingredient of the endothelial cell-derived relaxing factor. And it's used therapeutically to treat disorders resulting from ischemia. And when you have ischemia, that results in hypoxia. So you have decreased oxygenation to tissues. Those tissues are going to die. That's called ischemia. So one of the disorders that results from tissue ischemia or hypoxia is called angina pectoris. It's a cardiac disorder characterized by these acute episodes of real crushing chest pain that's secondary to an MI, myocardial ischemia. The myocardium, or the muscle of the heart, isn't getting enough blood. If it's not getting enough blood, it's not getting enough oxygen, which means that the heart muscle is crying in pain for that fuel. And when it's dying, these people grab their chest and they make a fist. That's because it's this tightening type of feeling. It's crushing. It's also accompanied by a shortness of breath. There is usually no permanent damage to the myocardium of patients who experience angina by itself, because it's really could be just temporary. So they can put nitroglycerin under the tongue, it dissolves, and it opens up the blood vessels, driving more oxygen and blood to the heart. Now, there's three different forms of angina. There's stable angina, unstable angina, and variant angina, which is called Prinzmetal's angina. Now, stable angina pectoris occurs only after physical exertion. The person mows the lawn, they take out the garbage can that's heavy, and then all of a sudden they're getting chest pain. That's pretty predictable, right? Unstable angina can occur during physical exertion, and it can occur at rest. So this type of angina has that strongest correlation to a future myocardial infarction. It's also the most dangerous. The Prinzmetal's angina, or the variant, only occurs at rest, okay? Only occurs at rest. Okay, I'll take a break. When I come back, we'll talk about the recycling and the lifespan of a red blood cell.